Hello everyone, thank you for joining me here for this topic. I'll be trying to guide you into an introduction to steel structures. You found this video as it was linked for you in your course notes or through our Brightspace page. Thank you so much and let's get started. Lovely. So I think I want to start off first by showing you this montage, this time-lapse of the construction of a building on campus, on our campus. This is the ARC building, the Athletics Recreation Complex, I believe it's what it's short for, which is being erected, as you can see, using steel as the main structural component. It went up very quickly. That was over the span of just a few months. And that's one of the benefits of steel construction and why it can be so popular in Canada, especially when it comes to low-rise buildings, right? Typically buildings that are maybe no more than 2 stories high and that are repeatable, right? So not too complex. So think like a Walmart or a Loblaws or a Grand & Toy, that sort of stuff, okay? Most of the items that we'll be chatting about you can find in chapter 18 and 19 of our textbook. That's the 3rd edition of building construction. Also, what I'm going to do is I'm going to link for you at the bottom here some interesting videos that show you how hot rolled steel is made, or I should say shapes that are made from hot rolled steel are made. That distinguishes them from cold form steel or cold rolled steel. But anyways, check them out. I'll link them for you. They're quite interesting. This image you see now on your screen is during and after construction of a bridge in Scotland, the Fourth Rail Bridge. I'm showing this to remind us again that steel structures are convenient because you have to bring all the pieces that make up this steel structure to site. They're already measured, they're already made to fit together, and they're already the right thickness and so on. That's the thing about steel structures is by the time you bring them on site, they're ready to be erected and it can go fairly quickly, assuming that they're not too complex. This is what the Fourth Rail Bridge looks like right now, and you'd be interested to find out that its construction happened over about 7 years, starting in 1882, and it's still in use today. Lovely bridge. The other interesting thing about steel construction, in Canada at the very least, but throughout the world, is the reason it's so handy is because it uses the same shapes pretty much regardless of whether you're in Canada, a different country, a different continent. Now, the shapes' names maybe might change a little bit. Some of the details of the geometry might change a little bit, but pretty much all the same shapes are used throughout the world. I'm showing some of them here for you on the screen, and I think we'll go into a little bit more detail of some of the common ones used in Canada. So these are some of the examples of the shapes that we'll cover in a few moments. Let's start with the common one, so-called I-beams. Okay, these steel shapes, they're called I-beams because they look like a capital I with serifs at the top, right? The shape on the left is known as a W shape. More details in a moment about that. And the shape on the right is known as an S shape. They look the same, but they are somewhat different and they're used for different things. The shape on the left, the W shape, or wide flange shape, you'll notice that it's more angular, right? Its angles are for the most part at 90 degrees. Also, the top part of it, the flange, the hat at the top and the bottom, is wide. Okay, so this shape usually is used when you have other beams or joists sitting on top of that shape. The shape on the right, an S shape, you'll notice that its edges are more curved and gradual, and the flanges at the top are narrower. So usually these might be used as joist members or secondary structural members. So a whole bunch of these holding up a floor together, for example, with nothing else sitting on it other than the floor. So let's talk about wide flange shapes. These are also commonly known in Canada as W shapes. They are referenced in drawings or specs by the following format. You start with a capital W followed by a number, a multiplication sign, and another number. So for example, something like this. You would read this as a W200 by 86. The first number, in this case the 200, refers to the nominal depth of the shape in millimeters. The second number, 86, in this case, refers to the weight of the shape in kilograms per meter, or more appropriately, the mass of the shape in kilograms per meter. Generally, the depth of the section, its flange width, flange thickness, and web thickness are set up as follows. That's typically the convention. Okay? And a reminder again that the top and bottom horizontal portions, those are called flanges. If you're into fonts, they're basically the serifs for the capital I. The vertical portion of it, that's called web. Okay? Next shape, channels, or they're also known as C shapes. They are labeled as such. You start with a capital C, followed by a number, multiplication sign, another number. For example, this would be read as a C250 by 37, where 250 refers to the nominal depth of the shape in millimeters, and 37 refers to the mass per meter in kilograms per meter. The depth, the flange width, flange thickness, and web thickness are demonstrated as such. Next shape is so-called hollow structural sections. This is how they're known in Canada, or HSS for short. They can come in rectangular shapes like you see here, square shapes, or circular ones as well. Typically, they're referred to when you're labeling them. You measure the depth first, the width next, and then the thickness, because it's the same all around. So for example, as you see here, an HSS 203 by 102 by 9.5, it means that it's 203 millimeters deep, 102 millimeters wide, and its thickness all around is 9.5 millimeters. Angles next, or as they're also known, L shapes. They're labeled with a capital L followed by a number, a multiplication sign, and a number, a multiplication sign, and a number. So for example, this would be read as L76 by 64 by 6.5. Where the first number, 76, refers to the depth of the shape, the second number, 64, refers to the width of that leg, and then the thickness is 6.5 millimeters everywhere, okay? Pretty much, except for the edges. The depth, the width, and the thickness are labeled as such. Finally, I want to mention plate girders, okay? Plate girders are kind of custom-ish, if you will, shapes. Plate girders are basically I-beams, but they're not hot-rolled I-beams. Instead, they're made typically to suit, but not always, where you take a steel top plate, a steel bottom plate, and a steel plate for the web, and you weld them together to get an I-beam. They're usually used when you need a big beam to take large loads. So in this case, say if you're trying to transfer the load from that column so that it does not go all the way down to the ground floor, right? You want to make it open space, say, and you would insert a beam as such. By the way, do you know the difference between a beam and a girder? Structurally, they're essentially the same thing, right? They're typically horizontal members that resist shear forces, bending forces, and typically are not typically designed for compressive or tensile forces. But there is a fundamental difference between a beam and a girder, and I want to try to illustrate it here, okay? I'm calling some of these elements beams and some of these elements girders, okay? A girder basically is a large beam like this one here that is supporting other beams that frame into it or are supported by it like these ones here, okay? So a simple way to know what a girder is that a girder is a beam that supports other beams, okay? And a girder typically is connected from one column in the structure to another column in the structure. Similarly, when it comes to open web steel joists like these, the difference between a joist and a joist girder is that the joist girder is deeper and it supports other open web steel joists sitting on it, okay? And again, a joist girder connects from one column to the other, whereas a simple joist, a simple open web steel joist, goes from a girder to a girder or a girder to a beam, okay? So this is what an open web steel joist looks like. This is a photo I took in the early construction stages of the OWSJ Convention Center. Excuse me. And you can see that basically what this shape is there's very non-technical. There's a long top line, right? It's made of steel. There's a long bottom line made of steel, and then a whole bunch of triangles between the two, okay? So this is another view of open web steel joists in the construction of this building. And here's a more detailed view of what it's made of. An open web steel joist comprises the top line is called the top chord. The bottom horizontal line is called the bottom chord. And basically the triangles that are made between the two, those lines, they're the webs. Remember how we talked about webs with the I-beams? Okay, they're the vertical portion of a beam. Well, these are called open web steel joists because the majority of their web is missing. Compared to, say, a solid I-beam or a solid steel beam, most of this structure's web is empty air. It's nothing, right? According to the SJI, they're typically available in 3 categories. There's the K series, the LH series, and the DHL series. The K series is the most popular and is made to work in most common applications. The LH and DHL series are meant for long and/or deep applications, right? For more custom, out-of-the-box type of applications. A bit more detail about their construction. I took this out of your textbook, figure 1819 of the 3rd edition of your textbook. You can see that the webs can be made out of the crimped angles, where the ends are crimped. The top and bottom chords typically are made of L shapes side to side, back to back. And sometimes the webs can also be made of a rod that goes from top chord to bottom chord and so on and so forth. Another item in open web steel joists that I'd like to remind you of are known as the shoe. So this is the portion of the top chord of an open web steel joist that sits or bears on another element. Okay? So at the bottom of your screen, you can see 2 examples where an open web steel joist sits on the left on an I-beam, a steel beam, with its shoe. On the right, it sits on a plate, which then sits on a load-bearing bond beam in a CMU wall, concrete block wall, or reinforced concrete block wall. I'm making you aware of this so that you can see the difference. The other thing too that I'd like to let you know of is what the benefits and limitations are of open web steel joist compared to, say, solid steel beams. Because, you know, there are good things and less good things about them. Some of the good things about open web steel joists, they're lighter. Their weight is lighter because they're mostly empty air, right, compared to a solid steel beam. They're way easier then, as a result, to lift, put into place, and fasten where they need to go, okay? Also, these openings in the web allow also for the passage of pipes, electrical conduits, air ducting, and so on through the open web steel joist so that your ceiling cavity might be smaller. Some of the limitations, though, compared to a solid steel beam, because they're missing a lot of their web, right, it's empty air, they tend to be deeper than an equivalently strong W shape. they are not very good at supporting concentrated loads, which means loads that are localized as opposed to spread. And they don't work very well for irregular layout, buildings that have really weird layouts that are not basically boxes, okay? So the other thing that I want to talk about after open web steel joist is something that's shown here. Maybe not super obvious, but we'll get to that. Can you notice the difference between the photo on the left and the photo on the right? You can see sunshine through everything on the photo on the left, and the photo on the right, suddenly that sunshine is blocked. And that's because steel deck has been placed on the open web steel joist. See, open web steel joists on their own are not good enough to make a walking surface like a floor or a roof. You next need to put a flattening surface like a deck on top of it. And I mean something like this. The way that it's set up, this decking comes in sheets, and it's simply put one layer at a time next to each other, and it's perpendicular to the direction of either your beams or open web steel joists. The shape of your decks can vary, and I should also say that typically decks sheets are made by cold forming. So unlike hot rolling, which you've reviewed a few slides ago, cold forming is where you get a sheet of metal and you actually bend it cold to give it the shape. So I'm just trying to show you here, taken straight from your textbook, the different geometries that you can have in your decks, as well as nomenclature, like top flange, bottom flange, or flute, the deck depth, and what the web members are, okay? And again, just some more examples of what shapes can look like and how decks are fastened to the structure below, whether it's beams or open web steel joist. In this case, on the right, you see how a deck is fastened to open web steel joist by screws, by screwing it into place, okay, in its flute. Also, the other thing that you want to do then with your deck, the deck is not what you walk on. You typically would then put some reinforcing steel and then pour concrete so that you have a walking surface, okay? And now you'll see here two examples of a steel deck with reinforcing and concrete poured on it. And the interesting thing about this, especially of the top example, is you see that crimping in the webs of the deck, and that's there to make sure that the concrete bonds well with the deck. Otherwise, it might just slide off because it's smooth steel, okay? So this is what happens. After you put the deck in place, you would put reinforcing steel parallel and perpendicular to it. You would cap off the openings in the deck so concrete doesn't get inside that decking and under it, and then you cover it with concrete. Here's another example of a different portion of the Ottawa Shaw Convention Centre. You see here something a little bit different. Do you see those what look like bolts that seem to be fastened to the deck but not all the way through? They stick up. Those are called shear studs, and they're usually placed at the location of a steel beam under there. The purpose of the shear studs, which are connected to the steel beams under there, is to make sure that the steel beam, the steel deck, and the concrete poured on top of it all act together in a composite fashion, okay? Shear studs. So here, we're now at the point where we're ready to pour concrete on our deck, on our steel deck. And here's an image that shows you kind of what it looks like. I'm showing this image because it's important to point out that you want to make sure that you pour it properly, including vertical stops. Here's another image actually taken from the ARC building on campus at the college, just before concrete is being poured. And you can see here, there's a steel deck, steel reinforcing going one way and the other, and shear studs along the location of the steel beams. Anyways, I was talking about pouring concrete and having pour stops. Specifically, what I'm referring to, if you look on the left, is this L shape that can be typically fastened to a beam or similar, and it basically stops the concrete from pouring over the edge of the deck, right? Because that's the whole thing about concrete. You have to tell it where it must go, okay? And I'm just pointing this out too because it will help you with your working drawings, right? Getting full marks. So now looking on the right, here are two examples of pour stops. The top one is anchored basically in the concrete, right? You put a pour stop with a bolt attached to it or a shear stud so the concrete grips to it. And the second one is actually welded in place. Just two different ways of doing it, okay? And here's a better view, I guess, a more easy to view schematic. Here is the pour stop, typically an L shape, that is put at the end of the deck so that when you pour the concrete stops at it, okay? All right, now bridging is important. When you put your open web steel joists in place, you want to make sure that all of the open web steel joists are braced with each other or bridged against each other. They work together. And that's done by bridging the space between every open web steel joist. And you can do this in one of two ways. On the left on your screen, you can see diagonal bracing, cross bracing between open web steel joists. And on the right, you see examples of horizontal bracing between open web steel joists. When do you use one or the other? Typically, if the span of an open web steel joist is more than 15 meters, you use diagonal bracing. If the span of an open web steel joist is less than 15 meters, you use horizontal steel bracing between open web steel joists. That's simple. Okay, and I guess the last thing that I want to chat about as we come to an end is end spans. I'm looking now at the roof of a structure, and it looks like it has a CMU wall on one side. And this is the end span. It's the space between an open web steel joist and the side wall, okay? That end span must always be bridged, especially if it's going to a CMU wall, okay? That's it. That's it. We've reached the end of our lecture. I hope this helped a little bit. Check out below for links for the next videos that I created, kind of going over how to determine the depths of members and the alignment of directions, and hopefully that will help you with your first project for working drawings. Thank you so much for your time, and have a lovely day.